Great pleasure to introduce to you someone that you know very well, Dr. Dendukuri. Dr. Dendukuri is the director of the Technology Assessment Unit here at the NUHC. She is an associate professor at the Department of Medicine and an associate professor at the Department of Epidemiology, Biostatistics, and Occupational Health. She has done great work in the Bayesian area of research. She has a Ph.D. in biostatistics, graduated from McGill, and did her postdoc at Harvard. And she's been like very active in the Bayesian research, especially on diagnostic testing. And this is what we're going to hear about today, right?
So thank you very much, Elham. Indeed, Dominic here was asking me to send you my bio sketch, and I said, I've known Elham for 21 years. I hope she knows something about me that she can say. Okay, I don't know what in my pocket here. Okay. What is this? I don't know. Fine, we'll see. Thank you all for being here. I'm going to share with you some ideas on a topic that I've been working on for the last almost 20 years, since my PhD basically. And so the topic is on estimate when you don't have a perfect reference test. And in today's talk, I would like to convey to you the importance of dealing with this problem by quantifying the uncertainty in the problem accurately. That, in my mind, is the key to solving the problem. And over the years, I've written papers. I started off when I was younger. I was writing more papers in statistics journals, papers full of equations and about developing new methods, novel methods, as we call them when we submit grant proposals. But then, over the years, I've really come to feel that, well, all our good work is in statistics journals and somehow not propagating beyond those journals. And I would like to do more to explain the methods to a wider audience. And so, along that trajectory, we've published some papers. Here's a paper by Ian sitting in the back. There's some excellent work. We published it in Statistics in Medicine. And this is another paper published in 2016 with two students who were PhD students here, Samuel Schumacher, and actually a visiting student from the Netherlands, Martin van Smeden. So the work in these two papers from Statistics in Medicine and American Journal of Epidemiology forms the basis of my talk today. We're actually right now working on going a step further and trying to publish this work in a medical journal. That would be an achievement for me. And we've been, of course, very lucky to receive support from CIHR, FRSQ, NSERC, and this Dutch organization as well along the way. And I'm going to talk about three broad ideas in this talk. I'm going to first present to you a motivating example to explain the methods. It's the problem of childhood TB, testing for childhood TB. Then I'm going to talk about composite reference standards, which are one way of approaching this problem of estimating diagnostic test accuracy, and you'll widely see that in the literature. And the third part of my talk is on latent class analysis, which is the method that I have worked with most. So a few words on childhood TB. This is a disease for which there's no perfect test. And so it's illustrated here in this diagram. So let's assume that this black circle represents children who have true active TB whom we'd like to identify and treat. Only a small fraction of them are identified by microbiological tests like culture. And those tests have very high specificity, and they would be a positive test on culture would be considered essentially proof that the child has TB. But very few children are identified like that. So you're left grappling with other sources of information. Whether the child has symptoms and signs of TB, whether they have had contact with a TB patient. So if the child's parent has TB, then clearly that would be a potentially important source of information. The culture test is negative, but there is a parent who has TB, and that would probably prompt a physician to consider treating the child. Other pieces of information include immunological evidence, such as information from the tuberculin skin test or interferon gamma release assay tests. In some settings, you might also have access to a chest radiograph. And all of these other measures that I'm talking about, as you can see, cover a area beyond that circle of active TB. In other words, they are sensitive. They might pick up cases of active TB that we're interested in, but they also will pick up other conditions which are not active TB. They have poor specificity. Nonetheless, there is a general belief that using multiple diagnostic tests is important because you want to increase your diagnostic yield. You want to catch those kids who are being missed by the culture test. But what you can see from this illustration is that no single test is considered adequate. And so if you want to evaluate a new test, then you're stuck with a problem of not having one reference against which to compare it. What do we do with all these multiple imperfect tests? Over the years, people have described scoring systems or composite rules. And what this graph illustrates to you is that these different rules um, don't necessarily agree with each other. So in this graph, I worked with 1, 2, 3, 4, 5, 6, 7, 8, 9 such rules that had been identified for childhood TB, took the same cohort of data and calculated what the number of children with TB is according to the different rules. So you have 9 rules, and essentially based on them, the prevalence in this cohort would have ranged from 6.9% based on one rule to almost 90% based on other rules. So in summary, these different rules are not in agreement with each other. They're discordant, and it's not clear what to do. So to address this problem, I mean, these researchers, groups of them have gotten together, and one of the most recent attempts in 2015, a clinical case definition for childhood TB was published to deal with the problem I just mentioned. And you can't see the fine text here, but they use the same tests that I mentioned before on my first slide: culture, the skin test, the chest radiograph. And based on all that information, they give you some general rules on how to identify children who have confirmed TB, those who have unconfirmed TB, and those who are unlikely to have TB. And the hope is that this kind of rule set up by a big group of researchers will influence harmonized classification, so that if you're doing a study in Canada and somebody else is doing their study in Hong Kong and someone else is doing their study in South Africa, they will all use this method, and thereby they will achieve a harmonized rule, and it will provide greater comparability across studies. Because right now, with different people using different rules, it's really not clear if we can compare results. And of course, a rule for classifying TB is then used to evaluate new tests for TB. So within that classification of TB, no TB, you can say something about the sensitivity and specificity of a new test. So that's the purpose of defining this kind of case definition. So we decided to, or at least in this talk, I'm going to illustrate to you what happens when you apply this case definition in practice. How easy or difficult is it to do? We will use in our example this cohort of children from South Africa. And indeed, actually, I didn't mention my very first slide. All this work has been possible because of very interesting collaborations. And so someone like me as a statistician couldn't hope to have access to this data except through working with Madhukar Pai, who put me in touch with Heather Zar, who shared this very nice data set. And in this data set, what we find is, where is this, the light thing? It doesn't work on this. Oh, I see. Okay, fine. So just roughly, what's I think interesting here, 749 children, 21% of them had HIV, 28% considered malnourished. So these are really sickly children, and they were all hospitalized, suspected for some kind of, I guess, TB or lung disease. And these are the results of the different diagnostic tests that were carried out on these children. So you can see 16% of them were positive on culture. But like I mentioned in my earlier slide, we suspect that more of them might be having TB than culture can pick up. And as we expect, the chest X-ray picks up a larger number, 33%. The skin test picks up 43% as positive. And many of them have somebody in their household who has TB, 55%. And then what is striking is here this last statistic telling us that whereas only 16% confirmed by microbiological test, 60%, almost 60%, 58% are treated, have gone home with the treatment. So, and as from my limited knowledge, TB treatment is, I think, quite a difficult treatment. It's expensive, it's long, and what these numbers tell us is that children are being treated on suspicion, and probably there are children who don't have TB who are being treated, but the risk is too great. Yes. I will actually defer to some people who know about TB to answer that question. I'm not sure. Is there a TB vaccination? There isn't. The BCG vaccination. The BCG vaccination. Okay. 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 Isn't the protection doesn't last? I think that's it's still a huge problem in countries like South Africa. 749. Yes. Some had negative diagnostic tests. Correct. That's right. That's right. These are the percentage positive. Yeah. The Venn diagram. Can you recreate the Venn diagram? There you are. It's not a Venn diagram, but it's a cross tabulation. Okay. All right. So that's right. So exactly like Ben said, what's interesting here is to look at if you want to apply that clinical case definition, especially what's the cross tabulation of the different tests that you observed. And the way I'm setting up this problem is as if we would like to estimate the sensitivity and specificity of the expert test, which at the time this cohort was being gathered was the kind of new test on the block that was interesting to evaluate. So the standard tests at the time were culture, smear microscopy, chest X-ray, the skin test. And if we follow that case definition that I put up earlier, then all the children who have microbiologically confirmed TB, that means culture positive or smear positive, they're all here, they're all considered confirmed TB. The children who are negative on everything would be unlikely TB. And actually, I've used an earlier definition that the same group had published to break up their unconfirmed TB into possible TB and probable TB. Okay, so those children who are positive on both X-ray and skin test would be probable. The remainder are possible, according to their gradation. So what should be our next step? If you want to evaluate expert, what's the next thing that your epidemiology 101 class tells you about estimating sensitivity specificity? We need to create some kind of a standard, right? We need to create some kind of a classification that will allow us to say these kids have TB and these kids don't have TB. But then when you look at this, okay, I think here the confirmed TB people were happy saying that they're all TB. At the other end, maybe because we have many tests, we can say, okay, yeah, for sure these kids don't have TB. What about this middle group here? What should we do with them? What would you do? Okay, okay. Right, okay.
How many of them are
there? Good question. How many of them are there? There are a sizable number of them. There's non-negligible number of them, not like 2 or 3 that you say, okay, I'll just throw that away. There's a sizable number there. Correct. So it would be interesting to have some extra information beyond just these photos. That's a valid point. But what I'm trying to get you to say is that indeed this group here would ideally not like to throw them away. We like to keep that information, maybe gather some more results on them, but somehow use them, not just get rid of them. But often one of the choices that people make is to lump this possible and probable TB with the confirmed TB to define what we would call a composite reference standard. And a composite reference standard would then identify these children who are negative on everything as no TB, but children who are positive on at least one of the other tests as TB. And then from this point onward, you can construct your 2 by 2 table and get your sensitivity and specificity estimate. And so that's what I've added for you here. It's not exactly in the 2 by 2 format, but you can see, but you have essentially a comparison between expert positive or negative versus the composite reference standards, no TB or TB classification. And that allows you to proceed. And like I was to Andrea's question, saying that here you see there's quite a few children over here in this probable possible group that you don't want to discard. Okay. So that's the background about childhood TB. And like I've just explained, you can see that in that setting, a composite reference standard seems to make sense. It would allow us to achieve our goal of estimating sensitivity and specificity of a new test. And in general, here's a definition for a composite reference standard. It defines a fixed, transparent rule to classify patients, subjects into disease positive and disease negative based on existing imperfect tests. And it's widely regarded as an appropriate method for estimating sensitivity and specificity. Commonly used rules are the OR rule. That's what I just showed you. That is, if any one of the tests is positive, then the child is considered disease positive. Or you can use the AND rule, which says that unless all tests are positive, I don't consider the child as being disease positive. And why do we use these composite reference standards? It's because we anticipate there's an advantage over using a single imperfect reference test. We think we're going to get a better classification of disease. Like I pointed out, the microbiological tests are not picking up all the TB cases. So the idea is that by adding these other tests, we're going to pick up more TB cases, and that's a better classification than just working with culture as a reference. Another terminology that you'll see when people describe composite reference standards is that you're told that they avoid what's called incorporation bias, because in the literature out there on composite reference standards or whatever scoring systems and so on, you'll find such situations where you have a new test and then you have the scoring system or rule, and the scoring system has been defined using the new test. Okay, so which of course makes the new test look very good because it has gone into the definition of what is truth, what is the disease positive and disease negative. But there are papers that have kind of discussed how to make a nice composite reference standard, and they emphasize that you must not put the new test into the composite reference standard, and that helps you to avoid what they call incorporation bias. So that's one anticipated advantage of using good rules for making composite reference standards. And then above all, people like the composite reference standard because they say it is transparent, it is simple, no calculus and gobbledygook, just simple rules everyone can understand, and then everybody across the world can do the same thing, and we can achieve standardization across studies. And providing a blessing to these ideas are some papers in the peer-reviewed literature. Here's a paper published in Statistics in Medicine coming out of the University of Washington at Seattle, reputed biostatistics department, telling you how using a combination of reference tests can be used to assess the accuracy of a new diagnostic test. So this paper kind of sets out how to make a composite reference standard. And here's another paper published in the BMJ. And this tells you that just the title is enough. It tells you the value of composite reference standards in diagnostic research. So you come away from this thinking, wow, this is good. This is a good method. And these established researchers use these methods. But in my opinion, there are a number of unanswered questions that remain about composite reference standards. Could you just put up that table? So if you look at the literature, there are the composite reference standards, across the literature, and this table is a very simple, non-systematic, review. Not a review, but anyway, it's just a little set of examples. So I found here composite reference standards for aspergillosis, chlamydia trachomatis, Clostridium difficile, pediatric TB, which is what we're talking about, prostate cancer, Parkinson's disease, pulmonary embolism, strep pneumonia. It's used in many, many conditions, because in all these conditions, basically, there's no perfect reference test. But one of the things that's striking is, you have to look at chlamydia trachomatis. You've got composite reference standards here made up of 2 tests, 4 tests, 9 tests. Again, a bit of what I told you for the childhood TB case. Multiple scoring systems and different rules. And for pediatric TB, the FDA has described how to make a composite reference standard using nucleic acid amplification tests. They suggest using 2 tests. So they're not considering household contacts. They just say 2 nucleic acid amplification tests, and you've got a nice composite reference standard. But you can find other examples. Here I have a paper published in 2014 described a composite reference standard made up of 8 tests. So in summary, our questions, Ian did the painstaking work here behind this paper. We were interested to know what happens if you increase the number of tests in the composite reference standard. Is a composite reference standard made up of 5 tests better than one that's made up of 2 tests? You would hope so, right? It could be with the or the and, but right, you would hope that even when you see that, in a sense, if we could find like a golden number and say that do not construct composite reference standards that have less than 5 tests, then that would be perhaps useful to know that, because right now you see people using all kinds of different rules. And the other thing that we felt that was missing in the composite reference standard literature was the concept of what happens when the composite reference standard and the new test make the same errors. Because after all, the composite reference standard is not perfect, right? It can make an error, and what happens when that reference and your new test make the same error? This is something that received a lot of attention in the latent class analysis literature. You cannot get a latent class analysis paper published without addressing that issue. But it seems to be absent in the composite reference standard literature, perhaps because people believe that by constructing a composite reference standard that does not involve your new test, then you don't have this bias. You have a nice clean separation by ensuring that composite is not based on the new test. So we started to look at this. Like I said, Ian did the math, which we put into a stats and medicine paper. And then we later followed it up with some simpler simulation studies with it, which I think make the same point. And that's what I'd like to share with you today. So we simulated data assuming we had a sample size of 1,000, that the disease prevalence was 10%, that we used an OR rule for the composite reference standard, and that the OR rule was based on tests that all had the same properties, just for simplicity, just because my point is just to convey a concept. We assume that all the tests have sensitivity of 70%, and as you'll see, we considered 2 settings. We allowed the test to have perfect specificity or to have 98% specificity. And then we said, how does this composite reference standard perform in evaluating the sensitivity and specificity of a new test, where that new test has 90% sensitivity and 98% specificity. And so we worked with the expected data set.
That's for the true disease prevalence?
Correct. That is correct. Was for the true. So these are the true sensitivity and specificity in each case for the true disease status. Right. So yeah, there's some places up here. So here's our my first little display. So like I said, we had 1,000 patients in total, and this table has the true disease status in the first column, the results of the test in the second column, and the observed frequency. So the first two rows are of the patients who are truly positive, and here you have the truly negative patients. Of the truly negative patients, let's look at this row first. I said this is the case where we have perfect specificity. So there's no false positives. There's no instance where the test is positive, and in fact the true disease status is negative. But the test has imperfect sensitivity, 70% sensitivity, and so of the 100 individuals who are truly diseased, only 70 were identified by the test. The 30 in red indicates that they were missed. 30 people were missed. So what happens if you augment this single test with another test and create a composite reference standard? So once again, the true disease status here at the extreme. This is the single test, and now a composite reference standard based on two tests. And so you can see that whereas this single test missed 21 plus 9, 30 individuals, the composite reference standard picked up 21 of those individuals who were previously missed. So there was a gain in using the composite reference standard. Specificity remains 100%, so no change at the bottom of the table. If I add a third test to my composite reference, then I get a further gain. I go up to 27, and now only 3 subjects are left undetected, and the lower part remains the same. So in other words, you see for every test added, there was a gain in the number of individuals picked up. But what if I have a high? Sure. Absolutely, please interrupt. No problem. Just tell me the time, though, somebody. Okay.
So each of these components of the composite test, I'm picturing each component with your original example of the true
Yes.
TB cases. If each of these
Right.
CRS components are independent of each other.
Correct. Yes, that's what we're assuming here.
This would happen, but if the test actually
kept picking up the same thing.
overlap the same
Yes.
thing, then they wouldn't.
Right. So that's a good point. So you're saying you're pointing out that this whole exercise reflects that the tests are independent of each other. Indeed, if, for example, my first test was culture and my second test was smear microscopy, which picks up only a subset of what culture picks up, then we wouldn't see this. But yes, we also looked at that kind of situations. But you're right, if two tests were correlated, the gain would be less. And so, but what happens if the specificity is not perfect? That's what this table illustrates. So let's say the specificity is 98%, not 100%, but not terrible. 98% is, I think, considered quite high. And I understand even tests like culture can have the occasional false positive. So what would happen then? So the top part of the table remains the same as we saw before when I add the second test. But now at the bottom, you have a loss in the sense that you've got 18 false positives. And if I add another test to my CRS, then that loss increases further to 35. So now there are 35 false positives because of that small drop in the specificity. So in summary, if the specificity of the component tests were 100% and the tests are independent, then yes, it's worth increasing the number of tests in the composite reference standard. But if there is a decrease in the specificity even by a small amount, you can quickly have an overall misclassification that's in fact worse than if you have a single test. So what does this do to the sensitivity and specificity of the new test? That's what we're primarily interested in. And these graphs try to illustrate that point. So on the tiny print, just sorry, but I'll try to explain. Top panel, sensitivity of the new test. Bottom panel, specificity of the new test. Dashed line in both cases is what we want to be at. That's the true value. And on the x-axis, you have the number of component tests in the composite reference standard. And I'm not sure what happened to my text over this. It's a bit mixed up, but I'll just say to you what I want to say is that the new test sensitivity is unbiased, basically. It's always estimated correctly, no problem. This is the case where we have 100% specificity. But the new tests' specificity is better estimated when you have 2 or 3 tests, and by the time you have 4 or 5 tests, you're estimating it perfectly. So this is the ideal CRS. You can see a clear advantage of adding more tests. But if you have the 98% specificity, then again, this is true test sensitivity, new test sensitivity and new test specificity, and the yellow line is telling you what's happening to the estimated values. And you can see that, okay, specificity, same story as before, add tests, you're doing better, but the sensitivity of the new test, you start doing worse and worse with every added test, which is a bit counterintuitive. So you're gathering more information and you are getting more and more biased results, basically. And then what happens if the composite and the new test make the same errors? So this addresses what your question here. So why would they make the same errors? Perhaps if they're based on, let's say, the same technology. Let's say if the composite reference standard is made up of nucleic acid amplification test, the new test is also of the same type, then in my understanding, these tests, certainly older versions of them, couldn't distinguish between live and dead organisms. They detect the DNA, but not the organism as such. So it's possible then that both the composite reference and the new test give a false positive. And we try to simulate this using these data here. So it's just like in the earlier simulations, 10% prevalence, and the properties of the new test and the component test remain the same as before. But those who are disease negative, we split them up such that most of them are in a situation where there's a high specificity of the test, but a very small percentage of them have that problem of a false positive, 35% of them. And by doing this, we retain the overall specificity at 98% by doing this. Okay. Now, what does this do to our simulation? Again, sensitivity and specificity of the new test, and we find that now, once again, the sensitivity of the new test is underestimated, and the underestimation worsens with every added test. However, it's not as bad as if we had all independent tests. Here in the lower panel, you see that the specificity of the new test is now overestimated. So the specificity of the new test looks better than it actually is, because it is making the same error as the reference, and we don't have a way of telling those two apart. Okay. In other words, basically this composite reference standard can, even though you think it can't have incorporation bias, it can lead to exaggerating the value of the new test. And this little simulation tries to look at what happens is are results really harmonized across settings, because this is one of the key things that researchers would like to have, comparable results across settings. So I think we took a CRS here based on just 3 tests, and once again it's sensitivity and specificity of the new test, but the x-axis is prevalence, true disease prevalence. And what we're trying to show here is that the estimated sensitivity depends on what the prevalence is. So if you were in a region where the prevalence is 5%, then the new test sensitivity would be 40% in the simulation. If the prevalence were in fact 30%, then the new test sensitivity would be 78%. So in other words, you take the same CRS, the same new test, and apply it in 2 different settings which have different prevalences, and you would end up with different estimates for the new test properties, even though in fact they are the same. And in other words, this approach is not helping us to achieve the standardization that we would like to have.
That's kind of what we're talking. Like FD101, where the
Yes.
prevalence.
Exactly, the prevalence shouldn't. And I have then seen papers that talk about, but don't you know prevalence actually can be affected by sensitivity, or rather sensitive and specific, or the reverse, sorry, sensitivity and specificity are functions of prevalence. But then I haven't gone and read those papers in great detail. It's possible. I think that it is possible. But I think what could be happening is this as well, that they are then, maybe they're not using, the tests are not perfect and not adjusting for that. Yes.
specificity of 98% is.
Yes.
Once you start using multiple tests clinically,
Yeah.
some of the examples you've shown,
Yeah.
that's actually pretty good. If we had multiple tests with specificities of 98%,
Right. Okay.
we'd be in business.
Okay.
No, but when you
Yeah.
start using multiple tests for chronic conditions, we're dealing with tests, I think, with worse specificity.
All right.
An example of TB and
Right.
ultrasound and
Yes. Okay.
tuberculosis, which is the we're not.
Okay.
It's even worse at
Okay.
clinically once we
Okay.
start to add multiple tests, especially with 4.
Yes. Okay.
Then it would really.
Okay. So, I think I'm going to skip that. That was just what I said before. What's happening here? With that those researchers who got together and made that clinical case definition, it seemed to make sense. Why is it? And that I think would perhaps be a good guideline for how things work in a clinic setting in practice. If you had a child in front of you whose parent has TB but culture is negative, maybe you gather a bunch of information and say, I'm going to treat this child. Maybe this kind of rule roughly represents what happens in that kind of setting. Then why is it that it doesn't translate into a good composite reference standard in a research setting? What's the problem? Any guesses? Mhm. Okay. Yes. Yes. Mm.
Right?
Yes. They have to. Yes.
I'm just thinking that we are missing the pre-test probability in a way.
Okay.
Or the
Yes. Yes. You're missing.
The
Yes.
diagnostication, so to speak.
Would have that.
Evaluate
Yes.
the
Yeah.
patient and
Correct. Yeah.
And Gestalt diagnosis, I think physicians in general consider to be quite informative. Again, it wouldn't be potentially as specific as the tools that are provided here.
Yes. So I mean, the word that what you say is the probability. There is a the problem is that the composite reference standard is assumed to be perfect, but it's in fact not. There's an uncertainty which is not acknowledged. We don't try to quantify it. When we make these simple rules and say this or this or this or this, then positive, so these people have identified that there's something called unconfirmed or probable or possible. But what's the numbers behind that? We're not trying to get to the numbers behind that. We're just making simple assumptions. Then let's lump it with TB. And that's, I think, the missing step that makes these simple rules work poorly. And the other thing is the interrelations between the tests are ignored. So you had in that, let's see if I can do this very quickly. Maybe not. No, I don't. I want to page up and page down, but okay. Here, look at this. We had almost some 16 possibilities between these 4 tests. But then we took it all and made it into just 2 possibilities, as if we had 1 test giving us a positive and negative. So in a way, we threw away information. There was interesting information here in the cross tabulation. Why is it that certain tests are positive together? That we just left out all that when we made a simple rule. And so you can see by that logic that if I had a 5th or 6th test, I'm throwing away more and more information. That's why that CRS does worse with added tests, because we're throwing away more information. And so how do we address the problem? The problem can be addressed by creating a probability model, something that gives us the tools to calculate that uncertainty. And we would need a probability model that for all of the imperfect tests that we're studying, including the new tests. So this is something people find counterintuitive, but we need a model that puts the new tests together with the old tests all together to study the interrelationships between them. We need to know when is the new test giving us information that was not there in the old tests. We need that cross-tabulation. We can't separate the two to get the results we're looking for. And this probability model would allow us to weigh information from the different tests using their sensitivity and specificity. So Clearly, I mean, intuitively, you know that culture test is positive, highly likely to be positive because you're thinking specificity is near perfect. We need the method that we're using, the statistical method, to do that. And we need something that will adjust for prevalence, conditional dependence between, that is the shared errors, and covariates, because there are more things than just these diagnostic tests that come into play. How do we define the probability for a single test? I'll just go over this with you guys. How do we set up that probability model? Okay.
What about disease severity? And again, might not be.
How
does that fall into the three different?
Actually, I think we'll have a nice illustration of it coming up. Okay. So how? I just want to talk about the single test, just to get you guys to think about this.
Probably a positive result.
Yes. What's the probability model behind that? Let's say just single test culture.
Can I use disease status as a
Yes.
like
Yeah.
the truth that's unknowable?
Right.
Whether the truth is
Correct. So that comes, okay, that's a factor. And but what's the the probability? How would you express the probability of the results of a single test?
it's a binary.
Yes.
So
Yes. Okay. Good. Good. Okay. Good. At least in the right direction. Now that I was looking for. So yes, you recognize that it's a binary thing. It's positive or negative. So it's rather like a coin toss. And what do we do to? How do we model coin tosses? We use the binomial density function. Right? This is what you learn in your introductory statistics course. The binomial density function has parameters which is the probability of a positive test, and the sample size. This is what's going into your model. That's all. When I say construct a probability model, that's all I'm talking about. It's not more fancy than that. But there's a small tweak over here, because the probability of a positive test in this case is determined by the prevalence, the sensitivity, and the specificity of the test. Why? Because the test is not perfect. So when you have a positive result, it's the probability of being a true positive plus the probability of being a false positive. There are two options there, and you need to consider both. And you can do a little bit of math and show that the probability of the true positive and the false positive are essentially related to are related to parameters that we're interested in, which is the prevalence, the sensitivity, and the specificity. And so the probability model is that binomial probability, and P is given by this. Now this is a simple case, one test. What if you have more tests? Then what happens? You have a multinomial distribution, right? So you want to take into account the patterns. So you have, like I showed you, we had 4 tests, we had 16 possibilities. Here with one test, we had just binary, 2 possibilities. If you have multiple tests, you keep increasing the number of possible patterns between them. So we need a probability model that will allow us to recognize that there are multiple patterns. But it's actually not more complicated. It's just a bigger model. But that multinomial model will also have probabilities. Those probabilities will be related to the prevalence and the sensitivities and specificities of the individual tests. Okay. So if you have multiple tests, you need a multinomial model. You would consider the sensitivity and specificity of individual tests. You can allow those sensitivities and specificities to be functions of covariates. So you can bring in other pieces of information. This is a very natural setup that allows you to expand and incorporate all of the different things that you do consider relevant in practice. And it would allow us to model what we call the conditional dependence between tests. So it would allow us to say culture and smear are more likely to pick up severe cases and less likely to pick up mild cases, and they're both likely to make the same error of missing those mild cases. So I won't write down the equation. I hope I've kind of conveyed to you the concept, how we build these probability models. That's all there is to it. So instead of making a simple Boolean rule saying this or this or this positive, then positive, we need to make that little extra effort to say, what's the probability density behind this? so that I can quantify the uncertainty in what we're observing. Again, can someone just tell me the time? Sorry. Should have brought my, thanks. So just quickly, the childhood TB problem, this is something we came up with, Samuel Schumacher and the clinicians who are working on this project, because again, statisticians, like, we love fancy models and equations and things, but if they don't make sense, if they don't reflect reality, then the model is nonsense. You can just get nonsensical results. So that how the conditional dependence structure arises, what are the covariates involved, is all very important details that is part of an interdisciplinary exercise to determine. So our observed tests are here: skin test, microscopy, culture, expert, and radiography. We hypothesized that there would be a correlation between the microbiological tests, especially. They're all dependent on the bacillary load. We hypothesized that there's multiple underlying conditions actually that we're detecting. Whereas the microbiological tests are clearly detecting TB, the skin test is detecting exposure to TB, not quite TB itself. And so you can incorporate all this into that probability model and bringing in covariates like household contact, HIV, malnutrition, and so on. And just very briefly, what it amounts to is that this is the table that you saw before, the cross-tabulation, the observed frequencies. And what it amounts to is we're saying that every cell that we observe is in fact made up of two unobservable parts: those who have active TB and those who don't have active TB. That's really what's going on behind this model. So you can imagine that there's, in this last row here, where all children were positive, there were probably more individuals here, whereas in this top row, this portion is the larger number. But essentially, using the sensitivities and specificities, that division is made for every one of these patterns. Just a word on that conditional dependence. So, like I was saying, it arises when both tests make the same errors, and we hypothesize that culture, expert, and smear are all dependent on the bacillary load. So, we modeled that by bringing in what we call a random effect. So we said that the bacillary load is something that's not measured, right? It's completely unmeasured, but we allowed it to be there, a random variable that would influence culture, expert, and smear. And this is actually not at all different mathematically from what you use when you're doing a longitudinal study or a meta-analysis, a hierarchical model, anywhere where you're trying to create dependence. Same math that you would use again over here. And by what we have here, so here's the sensitivity of these three tests: culture, expert, and smear. And this is that random effect, the variable that we introduced. So you can see when that variable is low, they all have poor sensitivity. If the bacillary load, which is what we're trying to represent by that variable, increases, then they all go up to have a higher sensitivity. Culture is the one that has the highest sensitivity. So you can see it's I forget what's the term here. The minimum detectable level or whatever is lowest for culture. You can see it. It detects faster, earlier than expert or smear would. So you can bring in that severity of disease into these models. These are the results of our latent class analysis. So if we had treated culture as perfect, then we would say that expert has 73% sensitivity, roughly. And if we had used a composite reference standard, that would have dropped to 22%. So if you know the 73% is probably an overestimate, it's only those very sick kids who are being picked up by microbiological tests. But if you go and put in chest x-ray and everything in there, you're going to get a very broad definition, and your sensitivity of this is going to plummet. And the thing is, in our work with Ian there, we found that unfortunately it's not even possible to say that the composite reference standard always gives you an over or an underestimate. Like, if we could do that, then at least it would serve to create a bound. But in this case, I think we can reasonably argue that this is an overestimate and that's an underestimate, but it's not always the case. Now here, this is the results of the latent class analysis. It provides a prevalence estimate of 26%. So 16%, remember, was culture positive, and it's suggesting that another 10% of kids probably had TB, were not picked up by microbiological culture tests. It gives us a sensitivity and specificity of culture, right, which is something, again, you don't get from the naive analysis. The sensitivity of expert now is around 50%, right, and that's, an important estimate there for anybody who's trying to decide whether to adopt this test in practice. And all the remaining tests as well, you get their sensitivity, specificity estimates. What's most interesting for me from this analysis is we're back again to that table that we saw before, the cross-tabulation of the tests, the composite reference standard, the new test expert, the observed frequency, and from the latent class analysis, we've got the probability that the child has TB in each of these cells. So if you line that up with what the clinical case definition said, then it's interesting to note that whenever the clinical case definition said confirmed TB, we generally have 100% based on the latent class analysis. There's some cases like this here. This, according to the latent class analysis, these children have only a 23% chance of TB, though they would be considered confirmed TB by clinical case definition. And the reason is that they are culture positive but negative on everything else. And the model is comparing that pattern, which is a very unusual pattern, very few kids have that pattern, to other patterns that were observed, and reasoning that these kids probably have a lower chance, but it's uncertain. There's an uncertainty interval all the way from 0 to 100 around that estimate. It's also nice to see that the probable TB group, 88%, 52%, is higher than the possible TB, 12, 9% over here, 56, 16%. So, in other words, there's no perfect reference here. There's no way to say this latent class model is perfect. We have to live with that uncertainty. But at least here, we're honestly admitting it and trying to, it's reassuring to see that it lines up with our prior guess as to what, the clinical case definition. And so that's it. You can look at those probabilities and you can see what we're missing when we either have the clinical case definition or the composite reference standard. We make clean classifications, but we're throwing away the uncertainty. And these predicted probabilities are also useful in another way. We compared these probabilities to the probability of receiving treatment. Remember, I said that these 60% of children in this cohort were treated. And if our model is correct, then it would suggest that children with as low as a 30%, this is on the x-axis you have probability that a child has TB, and on the y-axis the probability of receiving treatment. So it would seem that even children who have a 30% chance of TB have an 80% chance of being treated. So, yes. Right, absolutely. This is no judgment on whether it was appropriate to treat or not, but it's just allowing us to see that we're sometimes in a situation we're so uncertain, but we're exactly, it shows us where we're lacking information and quantifying that information. For what percentage of kids are we left in the dark like that and making decisions? Mm-hmm. Yes, well, yeah. I think they do smear first, which is cheap. Right. Correct. Yes. Right. So, in my brief answer to that is, if you want to fit a latent class model, then you need data from a research study where all tests have been carried out on all children or all subjects. That kind of data where we've made practical decisions, I'll do this, then I'll do that if this is positive. Basically, you've got a biased data set. You've got missing information. That's clinical practice, and you can use these models to inform those kind of decision rules. But you need to do this first. And yeah, so that's my summary. Latent class allows us to quantify uncertainty, and it's not without problems. It works well if you have multiple diagnostic tests, if you have complementary characteristics, right? If you have one or two diagnostic tests, it doesn't work so well. We know those problems well. But if you have more, like here we had 5 tests with this childhood TB database, which was really amazing. And right, I think I've said all this now. Yeah, it's I hear now about this interest in machine learning, and this is unsupervised machine learning. Yet you can see this. Then you hear about personalized medicine. Yet I think we're quite a ways away from the day where we're going to let a computer tell us this is 30% probability and then make a decision based on that. But maybe we will be there one day. And I'll just leave you with quotations from intelligent people. A long time ago now, James Maxwell, father of electrodynamic theory, stated, "The true logic of this world lies in the calculus of probabilities." Okay, and they cut out the preceding and following sentences, but basically his argument is Boolean rules, simple or and rules, are not representative of what we usually encounter in practice. We need to be able to quantify probabilities. And here's a quote from somebody much earlier on, Voltaire. I'm not sure it was made in the context of science, but I think it still holds. He said, "Doubt is not a pleasant condition, but certainty is an absurd one." Right. So to be sure that this child has TB, when you're actually not sure, well, you're not helping yourself to do correct analysis. So I'll stop there. Thank you.
Thank you very much, Nandini. We have 2 minutes.
Yes.
Can you validate this approach by finding historically some like old diagnostic tests that we used before the arrival of what we now consider to be like a real gold standard, and show that like that this modeling actually does more or less accurately describe the probabilities of even the subsequent.
Yeah. I mean, right. Maybe there are contexts that I'm not myself also am aware of immediately, but I think there will be more such examples as we develop better and better tests. Like say in childhood TB, tomorrow somebody comes up with the perfect test. It would indeed be very interesting to see how did this model compare with that reference. But then from what Anne just said, maybe that's going to take some time before we get to having high specificity models for a lot of.
I can think of all the tests that we would use to try to get to the true condition, or for having all the patients with the condition. That's such a high specificity. Once you're at 4 or 5 tests.
Yeah.
Because it's 2% of so 98%, usually the sensitivity is calculated in context.
Yeah.
I think it might even be worse.
Yeah. Okay.
Yeah. That's the reality.
Yeah.
Far from being.
All right, so I hope that keeps us in business for a while. Because I must say, I fear that I was watching iRobot in the weekend, and I was thinking, that's it, my job is over, and in 5 years we're going to be out, because it had a situation where a robot has to make a decision whether to save the life of a child or Will Smith, and Will Smith had 27% probability of survival, and the child had 11%. So it saved Will Smith, who was left bitter for the rest of his life. But that's what we do in technology assessment. That was probably the right decision, because Will Smith would have probably killed that child and himself. So.
I think the problem is, as clinicians, that we need to make yes/no decisions. That's stuff.
Correct.
This kind of uncertainty.
Yes.